Hi everyone. As our next topic for object detection series, we are going to be looking at SSD or Single Shot Multibox Detector. In the previous video, I covered YOLO V1 and initially I planned to follow it up with YOLO V2 all the way till YOLO V5, including YOLO V5 implementation. However, I decided it would be better to cover SSD first, just so that we follow the chronological order in which these object detection models were released. So for this one, we'll cover SSD. And then in the next video, we'll do the whole YOLO V2 till YOLO V5. So up till now, we have looked at methods from both two-stage and one-stage family of detectors. An SSD, like YOLO V1, is a one-stage object detector. Which means, like YOLO, there is going to be a single model generating all the boxes and their class probabilities for the objects present in an image. The specific mechanism of detection involves making predictions for a set of default boxes of different scale and aspect ratios spread across the image. So very similar to how we used anchor boxes for RPN in faster RCNN. If you aren't familiar with anchor boxes, then do watch the faster RCNN video first, where I talk about anchor boxes in detail. Given that default boxes of SSD are exactly like anchor boxes of faster RCNN, let's start with what we do in faster RCNN and see how SSD's approach is different. In faster RCNN, rather RPN of faster RCNN, we had a backbone which was VGG16 in implementation, and using the last convolution layer's feature map, we made predictions for a set of reference boxes of specific scales and aspect ratios, centered at the center of each of the feature map grid cells. Using 3x3 convolutions, we predicted if any of these reference boxes contain an object and also predicted transformation parameters to transform the reference boxes to tightly fit the underlying object. Like here, this 3x3 convolution output will be making predictions for the reference boxes centered at the center grid cell. SSD pretty much does the same, except two differences. First one is that rather than just predicting the probability that the reference or default box contains an object or not, we directly predict the probability score for all categories present in our dataset, including background. Secondly, we don't just make predictions for default boxes on the last feature map, but in fact use feature maps of multiple layers at different resolutions and make predictions for default boxes of different scales and aspect ratios for each of these feature maps. Here I have just shown the reference boxes at the center cell, but they'll be present for all the feature map grid cells. And during training, given an image and ground truth, SSD decides which of these default boxes should be treated as a background box and learns to classify those as background class, and which should be matched to a ground truth object. We'll get into details of this matching strategy later, but here assume that these two default boxes end up getting matched to the only ground truth box. Then SSD will be trained to classify the blue default boxes as car class, and also learn transformation parameters which transform these foreground default boxes to better fit the underlying object. This idea of using multiple feature maps is also something we saw in faster RCNN PyTorch implementation video, where using FPN, we extracted feature maps of different resolutions from different layers of the network. SSD does the same thing, except we don't have any FPN here, as FPN was published at a later date, and here the raw feature maps are directly used. This aspect of using feature maps from different stages of network to make predictions for default boxes of different scale, earlier layers used for small scale default boxes, and later layer outputs used for large scale default boxes. This was the key contribution of SSD, and it allows us to get higher accuracy while using a relatively lower resolution input than YOLO V1. And because of using lower resolution input, we also see an increase in detection speed. Aside from this, the authors also use hard negative mining to select difficult negative examples during training and extensive data augmentation to make the detector robust, both of which we'll see later in the video. The backbone of SSD model used by the authors is VGG16 with few modifications and additional layers. But this backbone can be replaced with any other model and is not really the key component of SSD. So we'll look at backbone specific details later. And for now, assume we have feature maps of different stages of network and take it from there. The model that the authors work with returns 6 feature maps of 38x38, 19x19, 10x10, 5x5, 3x3 and 1x1. Each of these are associated with default boxes of different scale, with highest resolution feature map covering small scale default boxes and the last 1x1 feature map having default boxes of the largest scale. The authors assign single scale but different aspect ratios to each of these feature maps. For now, assume that the scale is S1 to S6 for the 6 feature maps. Then same as RPN, 3x3 convolutions are used to generate predictions for all the different aspect ratio default boxes. So if the first feature map is associated with K1 reference boxes, then because the feature map is 38x38, SSD would generate predictions for 38 times 38 times K1, which is 1444 times K1 boxes from the first feature map. Repeating the same process for all the 6 feature map gives us these values. Now for each of these reference boxes, SSD will have to generate C classification scores, where C is the number of classes in our dataset including background, and also 4 transformation parameters. The transformation parameterization is exactly same as RCNN, which, just to review, given a default box and a ground truth box, are these 4 transformation parameters corresponding to center X, center Y, and width and height transformations. In implementation, both these predictions will be taken care by convolution layers. For the classification part, the convolution layer will be having same output channels as the number of default boxes at each cell times the number of classes, including background. As for each box, you have to generate classification scores for all the C classes. The other convolution layer, which will be transformation prediction for default boxes, will be having same output channels as the number of default boxes at each cell times 4 to predict the 4 transformation parameters for each of the default boxes. Now let's see what the exact values of S1 to S6 and aspect ratios are. In the paper, the authors provide the formulation they use for computing the scales for all feature maps. Specifically, the scale of default box to be used for feature map K is computed like this, where M is the total number of feature maps, Smin equals 0.2 and Smax equals 0.9. So basically, we use scale of 0.2 for the default boxes of first feature map, scale of 0.9 for boxes of last feature map, and for feature maps in between, the boxes are of scales that are equally spaced between 0.2 and 0.9. Let's take a specific case of 5 feature maps. So the first feature map will have 0.2 scale, last 0.9, and these will be the scales of boxes of the middle 3 feature maps. Keep in mind that when we say a default box of scale 0.2, we mean that its area in pixel space equals 0.2 square times the area of image. Specifically, if our image dimensions are 300 x 300, then boxes of scale 0.2 and aspect ratio 1 will be 60 x 60. And boxes of 0.9 scale and aspect ratio 1 will have almost the same dimension as the entire image. For the aspect ratios, The authors use the following set of ratios. So for scale SK, to get the box for aspect ratio AR, we set its width to be SK times square root of aspect ratio and height to be SK divided by square root of aspect ratio. This will give us width divided by height as equal to the aspect ratio, and area, which will be W times H, will be equal to SK square. So now for these 5 scales, if you compute boxes of aspect ratio 1, 2 and 0.5, then you will get these dimensions of default boxes using the same width and height formulation. For aspect ratio 1, the authors additionally add a default box of scale square root of SK times SK plus 1, where SK plus 1 is the scale of the next feature map. So this will roughly give us these additional boxes for each of the scales. For scale of 0.9, we'll be using SK plus 1 as 1. Once we have the scale and aspect ratios, then given a feature map, and here say we are working with 3x3 feature map as an example, the default boxes will have centers as this, where the denominator is just the size of square feature map, which is 3 here, and I, j will be having values of 0, 1 and 2. So effectively these are nothing but the center locations of each of the grid cells. The first center coordinate will be 0.5 by 3, which is 0.16 approximately in both the axes, and the last bottom right center coordinate will be 2.5 by 3, which is 0.83. If this feature map was associated with a scale value of 0.725, which is actually the scale ultimately used by the authors for 3x3 feature map, then for default boxes of aspect ratio 1, we would end up with these boxes. Now given an image with different ground truth boxes and labels, out of all these default boxes, we need to figure out which default box should be labeled as background and which should be labeled as foreground. And foreground boxes should be matched to which ground truth box, so that the network can be trained to predict the label for background boxes as background and that for foreground boxes as the class label of the matched ground truth box. And also for the foreground boxes, train it to generate the transformation parameters based on the ground truth box that is matched to that default box. So let's understand the SSD matching strategy for this. Based on the specific scale and aspect ratios used for all the feature maps by the authors, these are all the default boxes that we get for this ground truth image. Let's just keep a small subset of these for better visualization. The authors first find out for every ground truth box, the default box that has the highest overlap with that ground truth box. For these two ground truth boxes, we get these two default boxes. These are labeled as foreground with class label car for the larger one and person for the other one, and match to the respective ground truth boxes. Note that while looking for the best, we aggregate default boxes of all feature maps of all scales and aspect ratios. Additionally, they find all reference boxes which have greater than 0.5 overlap with any ground truth box. Those are also labeled as foreground. These are matched to the ground truth box with which they have the highest overlap. So for these foreground default boxes, the network will be trained to predict the matched ground truth boxes label as the class for them, as well as transformation parameters that transform these default boxes to the corresponding matched ground truth box. As a side note, this step of matching is very similar to faster RCNN, except for the foreground threshold. Now all the default boxes that were not selected as foreground are background default boxes for this image and this set of ground truth boxes. This obviously is a problem because the imbalance between the number of background and foreground boxes is going to result in a network which will effectively not learn to predict foreground classes. So here's where the authors use hard negative mining. They identify all the top K default boxes from this large number of background boxes which have the highest classification or confidence loss, and only pick those for training for background classification and ignore the rest. They use K as 3 times the number of foreground default boxes in implementation. So sort the background boxes according to classification loss in decreasing order and pick only the first K for training. We have seen how default boxes are matched to ground truth boxes. Now let's take a look at the loss with which SSD is trained. Similar to all models that we have seen so far, SSD is trained with a sum of classification or confidence loss and localization loss divided by the number of foreground default boxes in the batch. Starting with the exact formulation for localization loss, this is sum of losses over all foreground default boxes, so boxes that are matched to a ground truth box, and for each of these boxes, we compute the loss for the 4 transformation parameters and sum them. Each individual loss term is smooth L1 loss between the predicted transformation parameter for transforming the ith default box and target transformation parameter for transforming ith default box to jth ground truth box, assuming the ith default box is matched to the jth ground truth box. The targets are computed using the same formulation that we have been working with in RCNN variants. The classification loss is just sum of classification loss for all foreground or positive default boxes and classification loss for selected background default boxes as a result of hard negative mining. Now we'll get into how the authors use VGG backbone to end up with SSD model and what changes they make in VGG. So this is the VGG16 model, which is trained on ImageNet classification task with a stack of convolution max pool layers with activation, followed by 2 FC layers, FC6 and FC7, and a classification linear layer. The inputs to the final SSD model are images of size 300 x 300. The authors also implement a variation which works with 512 x 512 as input, but let's only work with the 300 case. For fine-tuning this network for detection, we first get rid of the classification layer. And as of now, the final feature map prior to FC6, FC7 layers will be of shape 9 x 9, and that after the Conv4 layers will be 37 x 37. The authors replace the final max pool, which is 2 x 2 max pool with stride 2, with a 3 x 3 max pooling layer with stride 1 and padding 1. So basically now the shape does not change after the last max pool layer. And we'll get a feature map of 18 x 18. Additionally, we also make a small modification to this stage 3 max pool operation to actually get us feature maps of 38 x 38 and 19 x 19 at these stages of network. We basically change the max pool layer to compute the output shape using ceiling operation instead of floor. Now the pre-trained FC layers are converted to convolution layers. The weights of FC6 layer is of shape 4096 x 512 times 7 times 7. This is because after the last max pool, VGG16 has adaptive pooling to convert the feature map to 7 x 7 shape, and the number of channels is 512. So 512 times 7 is the input dimension for FC6. FC7 is 4096 x 4096. We convert FC6 to a 3 x 3 convolution layer with 512 input channels and 1024 output channels. So this would have a weight of this shape. Similarly, FC7 is converted to 1x1 convolution layer with 1024 input and output channels. And for FC6, the authors additionally also use dilation. The parameters of these new convolution layers are initialized from their respective pre-trained FC layers. For instance, reshaping the weights of FC6, we have 4096 cross 512 cross 7 cross 7, and sampling 3 values from the last two dimension and 1024 and 512 values from the first two gives us the initialization values for this conv layer. And the same is done for FC7 to convert pre-trained FC7 to conv7 layer. After converting the FC layers, we add extra convolution blocks. Each of these convolution blocks are two conv layers with ReLU activations. The first layer being 1x1 convolution and second being 3x3 convolution. The authors set specific stride and padding for the 3x3 convolution layers to get the following feature map shapes from each of these blocks. We then use these specific feature maps and for each have our prediction convolution layers. These prediction convolution layers will be a 3x3 convolution for classification and another 3x3 convolution for box transformation prediction. The number of channels for each of these prediction layers will be determined by the aspect ratios. The scale for these are equally spaced values from 0.2 to 0.9, just like the example that we had seen. However, to get better on detecting small objects, the authors used the conv4 output, which was 38 x 38, to get the predictions on default boxes of scale 0.1. The aspect ratios for default boxes of all scale are 1, 2, 0.5, 3 and 1/3. But for the first and last two feature maps, the default configuration only uses 1, 2 and 1/2 aspect ratios. This specific configuration of these 6 feature maps, VGG backbone and these specific scales and aspect ratios is what the authors use for VOC dataset. And this is what we'll be seeing in implementation as well. So using these aspect ratios and scales, let's just calculate the total number of default boxes for which SSD will be making predictions. For the first feature map, we have 3 types of boxes at each location. But remember, for aspect ratio 1, we also predict boxes of scale square root of sk times sk plus 1. So we actually have 4 types of boxes. And there are 38 times 38 grid cells, which gives us 5776 boxes. Similarly, for the second 19 x 19 feature map, we have 6 boxes. For the aspect ratio of 1, we have 2, whereas for the other 4, we have 1 each, making it 2166. And similarly 600, 150, 36 and 4 for the last 4 feature maps. This gives us a total of 8732 boxes. Compared to YOLO V1, where we were making predictions for only 98 boxes per image, this is a huge number. For the extra convolution layers, the authors mention the exact channels and strides for them in the paper. Now we'll look at an implementation of SSD which uses the same configuration of backbone, feature maps, scales and aspect ratios as the authors use for VOC 2007. For the implementation, we have this config, where the dataset config contains the image sets of VOC dataset that we'll be using. For now, we'll only train on VOC 2007 trainval images. And the number of classes will be 21, with input images resized to 300 x 300. For the model configuration, we'll use the same value as the authors. For aspect ratios, for the first and last 2 feature maps, we have 1, 1/2 and 2, and 1/3 and 3 are added for every other feature maps. Scales are 0.2 to 0.9, equally spaced from conv7 all the way till last 1x1 feature map. and additionally 0.1 for the Con4 feature map. IOU threshold, which will decide if a default box is foreground or background, will be 0.5. Low score threshold is for filtering low scoring default boxes during inference. Negative positive ratio, which by default will be 3, is how many negative examples are selected during hard negative mining for every positive examples. How many boxes per class do we keep prior to NMS? And last is that post NMS, how many detections per image do we keep? Its default value being 200. Let's start with the dataset class first, because that will cover all the augmentations that we need to understand. In the initialization part, apart from specifying the file name for image sets, we also specify the ImageNet mean and standard deviation, as well as mean RGB pixel values. These will be used for normalization and augmentation. For our training transformations, we have the following list, which is same as what the authors use. This basically is going to adjust color, saturation, brightness, and contrast of the image. This zoom out is an augmentation trick that the authors specifically introduced to increase the number of examples with small objects. What we do here is take a canvas filled with mean image pixel values of width and height anywhere between original image dimension to 4 times that value, and place the image at a random location on the canvas. Since this will ultimately be resized to 300 x 300, training on such images will improve the model's capability to detect small-sized objects. Third is random IOU crop, and here we first sample from a range of IOU values and then take a random crop of the image such that the minimum overlap with the ground truth objects is the sampled IOU value. In this method, we first get a sample IOU and then keep on trying random crops till we get one that meets our required criteria. We have some other restrictions as well within this method, like aspect ratio of the crop should be between 0.5 and 2, and scale also should be within a range. Okay, then we have our horizontal flipping, and then resize to 300 x 300. Post this, we are doing some cleanup and converting to tensors. So this method will ensure that we get rid of all bounding boxes that are no longer valid, like say boxes that are outside of the cropped area as a result of IOU crop augmentation. And we also want to get rid of these from labels as well as difficult examples. Labels is the class label for these bounding boxes. So if we remove the box, then we have to obviously remove the corresponding index from the list of labels as well. And difficult is just an attribute tagged by VOC dataset for each ground truth detection, indicating that the object within that bounding box is difficult to recognize. So if the bounding box is filtered out, we obviously have to also filter out the difficult attribute for that bounding box. Then after converting the pixel values to 0 to 1 range, we normalize it using ImageNet mean and standard deviation. For testing or inference, we are only going to do a resize to 300 x 300 and scale and normalize the image. That's it. Then we get the classes, and this time also add background class. And then this method, which we have already seen in past videos, gets the annotation for each image from XML files of VOC. We just get the image set mentioned in the config, fetch all image names from corresponding text files, and then get annotations from their XML files. In getItem method, after fetching the image, we get its bounding box and labels annotation, transform the image, and then finally divide all bounding box coordinates with the width and height of image. So basically normalizing the box coordinates from 0 to 1. This is not really essential, And the only reason I do this so that during visualization, I can get actual coordinates by multiplying with original image height and width without worrying about if the network was trained with 300 or 512 sized input images. Okay, now to SSD model implementation. For this, I've basically taken necessary parts of PyTorch's SSD implementation and will be walking through that. Apart from few lines here and there and lots of comments, it's not much different from what happens in Torch Vision's SSD 300 VGG16 method. So this is our main SSD module class, which will load VGG backbone, extract different stages from it, add extra convolution layers as well as prediction heads. Then in the forward pass given an image, we'll get the classification and box transformation predictions for all feature maps, generate default boxes for the predefined scale and aspect ratios, and during training compute loss, whereas during inference do some post-processing like filtering and NMS. So we first load all the different config values like aspect ratios, scales and so on and so forth from the config. To the scales we append 1 just because for aspect ratio 1 we need to add additional boxes of scale square root of sk times sk plus 1. So this 1 will be used as sk plus 1 for the last feature map. We then load our backbone VGG model with ImageNet weights. To differentiate between Con4 and Con5 layers, we get the locations of where max pooling layer is present in the network. If you remember, I had mentioned that we need to make changes to the max pooling layer to ensure that the feature map dimensions match with what the authors provide in paper. So this line is exactly doing that, and it ensures that the Con4 layer's output is 38 x 38 and not 37 x 37. The input to this max pooling layer is 75 x 75, assuming the image is 300 x 300, and this seal_mode ensures that when PyTorch computes the output shape, it computes it as 38 x 38. Then we get all the layers till the 4th max pooling layer, excluding it. Now what's this scale weight for? So in an earlier paper on segmentation, the authors of that paper found out that when combining features of different layers, it's not only better to normalize them, but also scale the features. And for this, they introduced a per channel learnable scale parameter to scale the feature maps of a layer after normalization. This mechanism is also used by SSD authors, where before using the Con4 feature map for predictions, they normalize it and scale it. This 20 is the initial value of that per channel scale value. And the network is going to learn these per channel scale parameters through the course of training. Then these are the convolution layers for FC6 and FC7. Notice that we changed the max pooling from 2 x 2 with stride 2 to a 3 x 3 with stride and padding 1 to ensure that this max pool does not change the feature map shape. For getting the Con5 output feature map, we'll have everything from the 4th max pool till the 5th max pool, excluding that because we are going to add our own. Then this new 3 x 3 max pool and convolution replacements for FC layers. Ideally, we should also sample and initialize parameters for this convolution layer from the parameters of FC6 and FC7, but here we don't do it and we still end up getting decent results. Then we add additional convolution layers to get 10 x 10, 5 x 5, 3 x 3 and 1 x 1 feature map. These are the exact convolution layers mentioned in the paper, including the strides and channels. Now we are going to create prediction layers. So this list will be used to figure out the input channel values for the 3 x 3 convolutions. These are nothing but the last layer's channels of Con4, Con5 with FCs and the added convolution layers above. For prediction layers, we first create the classification heads for all the 6 feature maps, each being a 3x3 convolution with input channels taken from the list above. For output channels of these convolution layers, since each feature map is associated with only one scale, we can just take the number of different aspect ratios, and that will give us the number of default boxes at each grid cell. This times the number of classes will give us the output channels. Notice that we do length of aspect ratios plus 1, because for aspect ratio 1, we also have an additional box of scale square root of sk times sk plus 1. So this plus 1 is to cater to that additional box. We do the same for box transformation parameter prediction head, except here we have output channel as 4 times the number of default boxes, catering to the 4 transformation parameters for each box. Then these lines of code are just initializing the convolution layers. Now let's go to our forward method. We first call self.features with the image input. So all the layers including and till conf4 layers. This will give us our 38x38 feature map. We then normalize it and scale it using our per channel learnable scaling parameter. This scaled output will be what is used for predictions. But to the later layers of backbone, so everything from conf5 layers, we'll continue to feed the original non-scaled feature map output. So this is what we do here, and get our 19x19, 10x10, 5x5, 3x3 and 1x1 feature map. This output list then just contains the list of all 6 feature maps from 38x38 to 1x1. Then we iterate over each of these output feature maps and call the corresponding classification and box transformation prediction layer. The classification output will be batch size cross number of default boxes per location times classes cross h cross w. So we reshape them to batch size cross total boxes at all locations of this feature map cross number of classes. Since the first feature map had 5776 boxes, this will be batch size cross 5776 cross 21 for the first feature map. Similarly, we reshape box transformation prediction to get an output of shape batch size cross 5776 cross 4 for the first feature map. And for every other feature map, we do the same. Then we just concat this list of classification logits and box transformation predictions. So this will aggregate boxes across all feature map and give us a classification output of shape batch size cross 8732, which was the total number of boxes across all feature maps, cross 21. And box regression deltas will be batch size cross 8732 cross 4. Next, we generate the default boxes using this generate_default boxes method, which receives the output feature maps, the aspect ratios, and scales. This list is going to hold the default boxes for all feature maps. We'll first create default boxes for a single image, and then because our images are all of the same size, we'll just duplicate that set of boxes as many times as there are images in the batch. So let's see how the 8732 default boxes are generated. For each feature map inside this loop, we get the desired width and heights of different types of default boxes. The first one is aspect ratio 1 and scale square root of sk times sk plus 1. Since its aspect ratio is 1, its width and height will just be the scale value. Then we go through all the aspect ratios and compute their width as scale times square root of aspect ratio and height as scale divided by square root of aspect ratio, so that their area is scale square and width divided by height equals aspect ratio. Now we set up the centers for all the default boxes. For this, we compute the grid of shifts using the formulation for center mentioned by the authors. Each of these centers need to be duplicated as many times as there are default boxes at each location. So we get the length of width height pairs and duplicate these shifts that many times. So as of now, we have center x and center y coordinates, assuming the image dimension is from 0 to 1, for all the default boxes for this feature map. We do similar duplication for the width height pairs, but this time duplicate them as many times as there are grid cells in this feature map. This will give us the width and height for all the default boxes in this feature map. Concatenating both of these will give us Cx, Cy, width and height for all default boxes in this feature map. And these will be the shapes for all the 6 feature maps. After this loop, we would have gotten default boxes for all feature maps, and concatenating will give us 8732 cross 4 default boxes. Here we just duplicate these 8000 default boxes as many times as there are images in the batch, and also convert the coordinates of boxes from Cx, Cy, width and height format to x1, y1 and x2, y2 format. This D boxes then becomes a list of default boxes with element at index I corresponding to the 8732 default boxes for the ith image in the batch. This list of default boxes is finally returned from this generate method. Now, depending on if we are in training or inference mode, we'll do things differently. Let's look at training first. During training, we would have to first match default boxes to either background or one of the ground truth boxes. Then for the foreground boxes, get the transformation targets for the box transformation predictions, and finally compute total loss as sum of localization and classification losses. In this loop, we do the matching. For each batch image, we do the following. Get the IOU between the ground truth boxes for that image and the 8732 default boxes. Then for each default box, first find the best ground truth box, which is the one with which the default box has maximum IOU, and set that as the matched index. So matches will be a list of 8732 assignments. Then all the default boxes for which the max IOU was less than 0.5 and hence should be marked as background, we select those and set their matched index as -1. So as of now, foreground boxes are those with matched index greater than equal to 0. Then since the authors also find the best default box for every ground truth box and mark that as foreground, we also do the same. We pick the best default box for every ground truth box and here update the match indexes of those default boxes as the corresponding ground truth index. So matched indexes finally will be a list of same length as the batch size, and each element will contain the matched ground truth assignments for all the 8732 default boxes. Then this compute loss method is called. Here also, we loop over all the batch images and then for each do the following. First, get the foreground default boxes, so those which have matched index greater than equal to 0, and update this number of foreground variable. This is going to be the n used in loss equation. Then for each foreground default box in this image, we get the matched ground truth box and get the transformation targets using this method. This we also saw in faster RCNN implementation, where we just convert both the default box and ground truth boxes to CX, CY, width and height format, compute the targets, and these weights are also same as in faster RCNN. So here we'll multiply by these weights, and then in inference we'll divide the predicted transformations by these weights. With the targets computed, we use smooth L1 loss to get the localization loss for this batch image and add it to this box underscore loss list. Then we get the classification targets for all default boxes. All boxes have targets as 0, so background class. And then we update the target for all foreground default boxes as whatever is the label of the matched ground truth box. The ground truth classification targets for this image are also added to this CLS targets list. Then we stack both the localization loss and classification targets to make classification targets of shape batch size cross 8732. Using the classification targets and classification scores for all the default boxes for all the batch images predicted by the model, we compute the classification loss as cross entropy loss. Note that as of now, this is for both foreground as well as background boxes. Then we use this loss value for hard negative mining. We get the number of hard negative examples that we need. So 3 times the number of foreground default boxes. Then sort the classification loss in decreasing order and pick the first k indexes, where k is 3 times the number of foreground samples. Before sorting, we clone and set the loss values for all the foreground default boxes to a very low value, so that none of the foreground default box indexes get picked during hard negative mining. Then finally we return localization loss as sum of individual localization loss for all batch images divided by n, which was the number of foreground examples, and classification loss as sum of classification loss for foreground default boxes and classification loss for hard negative background default boxes, and divide that also by n. This is all that happens in training within this compute loss method. During inference, we just do some post-processing like filtering, NMS, and transforming default boxes according to predicted transformation parameters. So let's quickly go through that as well. In here, we first do a softmax to get class probability for all classes for all default boxes. Then for each image, we do post-processing, filtering, and NMS. First thing we need is use the predicted transformation parameters to convert the default boxes to predicted boxes. So in this method, we get CX, CY, width and height of all the default boxes, scale the transformation predictions by the weights, compute the predicted CX, CY, width and height, and convert that to x1y1, x2y2 format. After this, we clamp to ensure the box coordinates are valid. Basically clamping the x1, y1, x2, y2 coordinates so that those values are always between 0 to 1, since our targets were also normalized from 0 to 1. Then we do filtering and class-wise NMS. For each foreground class label, we get the class scores for that class for all default boxes. Keep only those boxes which have score greater than our low threshold, and then out of these pick top 400. Once we have picked the top 400 default boxes for each class, on this aggregated set of prediction boxes, we apply class-wise NMS. And finally take top K detections per image. For each image, we get the predicted boxes, their scores and labels, and return this list of dictionary. Essentially, during training, only loss will be computed, and during inference, only detections will be computed. So this covers the entire SSD model implementation. On training with the default configuration of SSD on VOC 2007 TrainVal images, after 100 epochs of training, we get these kind of detection results. Notice how unlike YOLO V1, it actually does very well for small as well as closely grouped objects. In terms of MAP, I trained only on VOC 2007 TrainVal images, and I ended up getting a result which is actually higher than what's reported in the paper. But this is because I also included zoom out augmentation, whereas this result in the table is actually without that augmentation. With zoom out, one is able to get 2 to 3% improvement. From the results reported by the authors, you can see that SSD 512, which takes larger resolution images as input, performs better, which isn't surprising as it will definitely perform better on small objects, and even for larger objects, a higher resolution input will improve localization accuracy. But if we compare the SSD 300 accuracy, in spite of being a one-stage detector, its accuracy is very close to two-stage method of faster RCNN. And with adding more data, it even gets better. And when you compare with the previous YOLO V1 detector, SSD is faster as well as better than YOLO V1. With YOLO V1, we get 66 MAP and a speed of 21 FPS. And SSD with 300 input resolution gives us 74 MAP and a speed that is more than double of YOLO V1. With 512 sized images, the MAP improvement is much more significant while having an inference speed that is almost same as YOLO V1. Through their ablation experiments, the authors also demonstrate the impact of some of the aspects of SSD model as well as training, specifically augmentation, using more types of default boxes, and dilation. The most significant impact is that of augmentations, where you can see that adding augmentations leads to almost 10% improvement. And note that this is without zoom out augmentation, which the authors experiment with separately and find that it leads to another 2 to 3% improvement. Starting with only 1 aspect ratio boxes, once we add 1/2 and 2 aspect ratio default boxes as well, we get about 2% improvement in MAP. And then adding 1/3 and 3 aspect ratio boxes improves about 0.6%. Using dilation for conv6 layer, so the convolution that replaced FC6 linear layer of VGG, does not lead to significant MAP difference, but it does make the network faster. The last result that we are going to be looking at is the impact of using different resolution feature maps. The lowest MAP is what we get when we just use one feature map for prediction, specifically the conv7 feature map. That was the convolution layer replacing FC7 of VGG. This drop is not because SSD will now end up making predictions for fewer default boxes, because the authors try to keep the number of default boxes same, no matter how many feature maps they use. This is done by having default boxes of multiple scales predicted from a single feature map. But in spite of number of boxes being more or less same, when we keep including more and more feature maps, the MAP keeps on increasing. So this improvement is indeed by making use of different scale feature maps, which give SSD a better chance of making accurate predictions for different scale of objects. Earlier layers for smaller objects, as it benefits by making use of higher resolution feature maps for predicting small objects, and later layers for larger objects, as it enables the 3x3 prediction convolution to have a larger context. And that wraps up everything about SSD. So in this video, we looked at how SSD brings in concepts which we have already seen, specifically one-stage detection of YOLO v1 and anchor boxes of faster RCNN. And by using multi-scale feature map, gets a higher detection accuracy with even a lower resolution input, thereby increasing detection speeds. If you are interested in object detection, then do check out my object detection playlist, which ultimately will cover everything from RCNN to YOLO v8. Hope that after this video, you now understand all details of SSD. In the next video on this series, we'll be looking at YOLO v5 and implementing it from scratch. Thank you so much for watching, and I'll see you in the next video.